In this video lecture, we're going to talk about how do we deal with noise. Now, y'all have had good experience dealing with light noise, but think about your spectra. Think about the noise that we see near a baseline. How do we deal with it? Now remember, if you're seeing all that light noise from your smartphone build, just think about what an instrument's having to do with. But when you think about the spectra that you've seen, has it looked very noisy to you? Is that because there's no noise or because we're dealing with the noise in some way? Now, how do we deal with noise? Well, like we do with a lot of things in this class and with science in general, we deal with it with math. One of the most popular ways to deal with noise is to simply average it out. You want to remember that noise oftentimes is random in nature. And if it's random in nature, we can think of it as being random error. And we can improve random error, or when we say improve, we mean minimize, by averaging more and more data points together. So if we look at the top of this figure that's in Harris, we can see that if we zoomed in to a spectrum with a fairly low absorbance, look at that absorbance value, 0.0001. You can see how noisy the peak looks and the super zoomed in appearance of A. The noise, again, that kind of random up and down motion. Now, how do we smooth that out? Well, if we look at the bottom of the graph, we can actually average some adjacent points together to smooth it out. Now, we wouldn't want to average, say, too many data points together because then we'd have big gaps. So if you look at really noisy data, and then you look at something like 9-point smoothing, you can see that, you see how there's actually less data points than 9-point smoothing? That's because if we look down at the noisy data, how we're smoothing it is we're taking clumps that are really close together spatially, we're averaging the values together, and we're going to plot the averages. Remember that averages are averaging extreme values together to get some midpoint value. So averaging is going to help us reduce noise. We know that based on what we've seen with kind of big variance. So we can do those smoothing. Now, the more points we average, the smoother our data. And we see that with this figure from our real noisy data to a 5-point smoothing, which has improved quite a bit. But then when we go to a 9-point smoothing, you see how their variance is quite low between those clusters. Now everything looks like it's conforming to the spectral peak line very nicely. The data has been smoothed. It is less noisy. Now, the types of noise that we're talking about right away is we're dealing mostly, and I just say mostly because there'll be some other types of noise, but our big type of noise that we've got to manage is your normal random Gaussian noise. This arises from such causes as just random motions of electrons in a circuit. As I've said in class, anytime that you have an electronic piece of equipment, those moving charges are just going to come with this type of random noise. Now, we've also got other particles that are moving in these types of systems. We've got the quantized nature of charge carriers and photons. This is called shot noise because it's quantized in discrete values. So this is what we kind of think about when we think about that white noise. It's random. We see a lot of clustered variance, but we see it up and down random movement. You can never get rid of this noise, but you can minimize it, like we did in the last graph where we talked about averaging. You can also use some other tricks that we'll talk about in this lecture. Now, a second type of noise gets us more into kind of a gray area between your systematic and your random. It's called drift noise. And it's also called inverse frequency noise, or 1/f noise. It's greatest at zero frequency and decreases in proportion to the inverse of frequency. Example of this is your flickering or drifting light source. So remember, all lamps have a limited lifetime and they are going to start to fade. Remember, for a lot of lamps and lamp sources, that you're effectively burning this material that is giving off light. You're consuming it in some way, you're exciting it in some way, and there is going to be a limited number of times, a limited lifespan of the material. So if you've got, say, a classic tungsten bulb with a filament, there will become a time, we've probably all changed light bulbs, and we know that all good things must come to an end. Now we like to think of an abrupt kind of, oh, the light bulb blew, but it actually starts to drift into decline, and it happens very slowly. So the average person isn't going to notice for, say, the preceding 30 days that the light has gotten a bit dim, maybe even a few months. But if you were tracking that in some way, you'd see that it was starting to drift from its maximum output, and it would go to a decline, and then it would quote below. Now this can be charged by a lot of things. In our instruments, we can think about changes based on, again, the temperature. Oftentimes in the types of bulbs that we're using either directly heat, we're using heat dispensation that occurs because you're shocking it with electricity. There's just age, wear and tear, and then there's just the variation of power line voltage, which is oftentimes in science labs why things are grounded very specifically so we can minimize this type of variation. But all of these things, again, they have a lifetime, and they're going to fade into that good night. And that means, however, we'd probably want to track that. So this kind of drift can be detected by running standards. You run them when stuff's super new, get a nice, reproducible, reliable response, and then you regularly run the standards over the lifespan, and you can start to see when your standard values start to deviate. That's not because of the standards, that's because of drift. Now we can correct for that in some ways if it's drift where we can actually fix a component, and the fix might be a replace. So think about your UV vis. We don't chuck the whole thing if the lamp starts to go. We just take out the light bulb and put in a new one. Now this is how you know that this is going to happen, is you're going to use a control chart. You're also going to, in a UV vis spec or in any kind of spectrometer with some type of a source, you're going to control that by tracking its output over time. Now you can do this by tracking lamp hours or how much time it's on. A lot of instruments will actually, when you put in a new lamp, you say, hey, start tracking, and every time the instrument's on, it'll start tracking the hours. A lot of time manufacturers will actually put a lifespan on a bulb. I'm sure even the bulbs around your house will say about how many days, years, months, hours that you can run this thing. Same thing on the light sources we use in specs. But don't take their word for it. You want to actually see how is it responding over time, because your conditions in your instrument and what you're doing with it might be different than your manufacturer. So you're going to want to run those standards, again, assemble a control chart, and see when this drift starts to occur. When do you start getting deviations from the values you expected when everything was sparkling and new? Now, here's our line noise / interference / whistle noise. This is going to occur at very specific frequencies, and it has to do with the environment around the place. Now imagine, think about the St. Edward's campus. There are certain types of day in JBW North and South, say between 9:50 and 10 a.m. You've got a lot of students moving, emptying out from one space and moving as a big group to another. That kind of movement of particles / people is going to occur with some discrete frequency. at a specific time. You can actually track that, and really sensitive instruments will pick up that kind of noise. For example, Harris talks about how you can actually see the frequency of 100 students exiting a lecture hall. Now remember, the instruments that we're working with, especially some of them like a high frequency, high field strength NMR, could actually pick up this type of noise, which is why they're designed the way they are and kind of buffered in this weird, what we think looks like some kind of weird pod-like housing. Well, it's because it's got all this noise. It also explains why a lot of NMRs and other noise-sensitive instruments are oftentimes in kind of separate rooms at the end of a hall, or maybe they're in a basement and they're kind of got really thick bunker-like walls and they've got double reinforced floors. It's because of this type of noise. You'd never want to install one of these instruments, say, over by Ragsdale, right? When you've got a lot of movement and big lecture halls. So we have to think about where we're going to place an instrument, how much traffic it's going to get, and how often, say, people are opening doors, big herds of people are walking by, all kinds of stuff. You also want to think about where is, say, the air conditioning vent, or is there some secondary instrument that's got a lot of noise to it? So think about in JBW North where the NMR is compared to where all the other analytical instruments are in 104. That's not an accident. That's because the NMR is that sensitive that we need to separate it from other instruments that are, quote, noisy, especially our mass spec instruments that have to run under vacuums pumps, which are really, really noisy. We've also got things like sonicating probes, which can be super, super loud and have really outrageous frequencies. You wouldn't want the instrument to pick up that. That's kind of more of a systematic error, though. Once you see that repeating discrete pattern, you can figure out the source of it and just limit that kind of noise. Very easy to fix. Again, one way to do that is you're going to electrically shield things. You're going to ground things, right? So thinking about power sources, if you live in a place that's got kind of fluctuating power grid issues, you don't ever want to put all your instruments in one electrical bay. Again, you're overwhelming the system. It could cause some type of electrical issue. And then too many instruments adjacent to each other, they're literally going to start picking up each other's noise, because again, these are sensitive detectors. So we've got to be careful with our instrument placement. Now, when we think about the internal workings of a spectrometer, let's think back to our UV vis, where we had, say, your double beam instrument. Your beam chopper is going to allow us to do some really cool stuff. Now remember, that beam chopper is what actually splits a single light source, one bit of it cohesively, so we're not losing any intensity. So it gets that beam chopper together with the mirror so that we can have that constructive wave behavior. So we get the equal intensity incident light going from the sample, through the sample, and through the reference. But all of that's controlled by a motor. And as soon as you start adding motors to something, besides cost, maybe your parallel thought should be, hey, how noisy is that motor? I don't know about you, but motors I can hear, right? You can hear when your computer is struggling, right? You can just think about all the things that are motorized around your house. Ugh, like your blender. Oof, that's a loud one, right? You wouldn't want to put a blender near an NMR, but you definitely know it. But your motor, anything that's motorized, that's doing this cool stuff, it's really helping the instrument, and that's how we can do this beam chopping and have a double beam. But you've just introduced a new noise source. So how are you going to get rid of it? Because we're all about getting rid of noise or minimizing it to a huge degree. Well, it's actually pretty easy. Your motor runs at a particular frequency. We are going to just pair it with a high frequency detector. So it doesn't even hear it. It's quite brilliant, actually. So we're going to run the detector. It's going to be sensitive, right, to certain frequencies, like those that would be transmitted from the light source or even emitted from the sample, depending if we're doing a emission or in a transmittance type environment. And then our motor frequency, though, going to be completely different than the frequencies we're actually interested in from our light source going through our sample or from the sample themselves. So if we pick a right detector, it won't even pick up the noise. So it's not even noise. It doesn't hear it, so it can't be noise. It's pretty brilliant. Now we can do a lot of tricks with getting rid of noise. You all know that. Just think back to your spec builds and think of all the things that you did to get rid of the noise. You blacked out the interior. You draped things. You taped things. Right? You made entrance slits and exit slits. Both. You did all kinds of tricks. And we do the same type of stuff. Another great thing we can do is a very nice instrument called a low noise spectrophotometer. Now, this looks very much, and it should, like a double beam instrument, because it is. But the fanciness of this one is that we do have two detectors. Now remember, I've talked about how we're not typically, with our double beam instruments, we don't have two detectors because we're just going to have the one. The reason why we don't have the two detectors is cost. Cost. We can certainly do it, but it's going to cost you. Now, why would you want to do it? Well, it's got to have a payoff. And the payoff here is beautiful. What you're going to do is you're going to have a detector that's for your reference, a detector that's for your sample. You're going to look at the difference. What that does is literally cancel out the noise. Because remember, your reference and your sample should be experiencing the same noise because they're trapped in the same environment. They've got the same motors nearby, the same electrons are moving around, the same photons are moving around, the same charge carriers are moving around. So they're feeling the same types of noise. So we can just subtract these detection signals from each other. Or really, when you think about detectors, remember how all detectors work. We're going to convert some type of energy, transmitted, emitted, it hits the surface of the detector. That is going to become current. Current, think of our equation, voltage, current, resistance. We're actually going to measure voltage. So when we get our two voltage readings, this is the actual easy part, is that we're just going to subtract them from each other. The costly part is actually fabricating and utilizing double the detectors. The voltage part, that's easy peasy. It's just more cost, but think about when you'd want to do this. When is the noise really going to be a pain for you? Think back to that first figure I showed you in Harris, the really, really low absorbance. Well, if absorbance is proportional to concentration, noise is going to be really, really tricky when we get to really, really low concentrations of sample. So if we want to work really on the low side and push LOD and LOQ in and below the floor, we're going to need to use an instrument like this. It's going to allow us to detect and quantify concentrations we wouldn't have even dreamed of before. So you might be thinking to yourself, oh, why do we spend so much time on noise? Well, here's a real reason. You look at this IR spectra at the left. It's kind of a mess, I'll be honest with you. I mean, look at the baseline. It's sloppy. It's slanting when we look at the left. The peaks are jaggedy. What's going on over there? Now, if you look at this one, that's what I'm talking about. That's the kind of IR spectra you want. Look at how nice and flat near the baseline, around 80% transmittance. You're getting a lot sharper peaks. Okay, you know definitely where things are coming from, kind of that baseline value. It looks a lot better. And that's basically why we spend so much time on it, because our signals end up looking better. And by better, we mean sharper, crisper, and we can make more confident analytical decisions. Here's the thing about noise. The reason why it's so important is because signal is dependent on noise. When we look at noise, again, we've got a lot of tricks, but one of the big ones is you're going to see a huge improvement with noise by signal averaging. So if we look at the very bottom, sorry, that's my dog, by the way. If we look at the very bottom, if we just collected that one spectrum, you can see how noisy it is when it's just the one. But if we start collecting multiple spectral runs and then averaging the runs together, we're starting to see with just 4 spectra averaged together how much the noise improves. Now if we take that up a notch and go to 16, that's getting even better. And look at the detail you're seeing now. When that one spectral scan, you don't know what that is. Is it one peak? Is it a blob? Is it even a peak? I can't say. As we get to 4, we start to see an outline of maybe it's a doublet of some type. Definitely by 16, I'm ready to call it a 2 peak. But woo, is that a 3rd peak showing up? Now when we get to 64 average together, you got that one broad peak kind of in the center, smaller one to its right, and then we've got almost a 3rd one peeking out. And look at how good it looks. Good meaning clearly there's something 1, 2, 3. Now the 3rd one, still I'd like to see a little bit more definition, some resolution improvement, but we definitely feel good now about those 2 peaks at 256. I mean, look at the increase in signal. You wouldn't have even been able to confidently call it a peak when it was just 1 spectra. Just going to 16, you can call it 2 for sure, and you're confident by 64. And at 256, you're definitely feeling it's 2. That's why we spend so much time on it, because our signal depends on the noise being minimized. The signal is measured from the middle of the baseline noise to the middle of the noisy peak. We define the signal based on the noise. So that's why we spend so much time on noise. Because look at this. How do you call a peak, and when is it noise? Well, you don't know that until you can actually see a big difference between the two. We couldn't see a difference between the two with just 1 scan, but we can see a big difference by 16 scans. You confidently say that it's got a discrete baseline at 16, and then right about center of the graph, that big broad peak, we can say, hey, that's significantly different than the baseline, and that's a peak. By definition, if we use this idea that signal is measured from the middle of the baseline, so you want to look at the very bottom and how those arrows, then we get a ratio of signal to noise of 14/9, and our ratio at that last graph, the bottom one, is 1.6. Well, you can't work with that. I think I've said in class a few times that the minimum signal to noise that you'd want is 3, because you need your signal to be substantially higher than your noise. If it's 3 times your noise, then you know it's in fact different from your noise, and if it's different from noise, it's a signal. Now, here's another way that we can deal with noise, or a common measurement of noise. A more common measurement, as Harris talks about, which requires a digitized signal and a computer, we use this equation called root mean square noise. Now the RMS noise is about 5 times less than the peak-to-peak noise measurement that we just did. In fact, if you look at the same data but plug it into the RMS equation, you're going to get a signal to noise of 7.8 versus the 1.8. That's madness. Let's go back and look at that. Remember that bottom one with just the one spectral scan, that's noise. I don't feel comfortable calling that a signal. But if we look at this equation and we do the math, we're getting real different values here. Exactly. What? Well, here's the thing. If we use RMS, the ratio again at the bottom is 1.8, and the signal to noise ratio is 7.8. But by our previous definition, the signal to noise ratio was 1.6. Well, it doesn't look like it's 1.6 to me. That looks like trash, or as we would say, noise. Well, Harris says, hey, clearly the signal to noise ratio depends on how you define noise. And I say, that's a huge understatement. You've really got to nail it down and be consistent. Again, look at that data. I look at that bottom graph and I don't see a signal. You don't see a signal confidently. I'm seeing hints of it at 4, but by 16, by 64, I'm feeling very good that that's a signal. The other thing I want to point your eye out to is if we look at the part of the graph that's nearest the origin, let's start at 256. You see how nearest the y-axis moving towards to the right, we've got that nice flat baseline we're end up seeing at 256. Well, if we carry that and we look at that first little bit of the graph and we just move our eyes down, you see how it becomes more and more and more noisy. That's the noise. Now look at the center of the graph where we see at 256 that there's definitely a peak there. So when I look at the bottom one and I'm saying I don't know if that's a signal or not, it's because I'm comparing it to the very start of the plot. And I'm not seeing a very clear difference between, quote, baseline and noise. Same thing goes to the extreme right, where again at the 256 line it kind of flattens out to a baseline signal that we're used to when we're talking about that's nothing, but the stuff in the middle is definitely a peak. Again, way down there at the bottom, that all looks noisy to me. It's not till we're up quite a bit in number of scans we're averaging that the real confidence comes in where you can call it a signal. So numerically, these two different definitions or way of calculating it are giving a real different view. But here's the thing. They probably also have very different cutoff values. If we use the other definition, the first one we introduced, and our cutoff value is 3, that works. But if we use RMS, I bet you the cutoff range is not 3 if that bottom one gives you 7.8. The cutoff is probably in the mid-20s to almost 30. So it's not quite a fair comparison. The thing is, we're going to have to decide on a single definition. You can't switch up the rules of the game in the middle of the game. Just like any other experimental parameter, we have to decide how we are going to define noise for a very particular experiment at the very beginning so that we can judge all data based on that definition. Excuse me. Now, when we take a spectrum and we record it and we add the results, so let's just say that we do 2 spectral scans. we add the results together. Well, if you just add the results together, then you're just going to get the same spectra and it's going to be twice the value, right? So if you collected n spectra, it increases the signal n times. Well, okay, but remember noise. It's not actually that additive. Like, oh, if I add 1 plus 1, I should get 2. Yeah, but remember, noise is random. And we're going to have noise attached to those spectra. And some of that noise is going to have positive values, and some is going to have negative values. If the n was recorded, the noise will be proportional to the square root of n. So that's why we don't add them together. We're going to average them together. And it's not going to be as easy as 1 plus 1 equals 2. Of course not. Signal to noise is going to be square root. Now maybe you knew that that was coming because, again, we've talked a lot about your random error and that kind of noise, or random noise. Remember, drift noise or shot noise, that's systematic stuff. We can find out the cause and get rid of it. This random noise, though, is our bigger problem. It's always there. We can't get rid of it. We can just minimize it. But remember, it's kind of very similar to random error, which we measured using significant deviation, which involves the square root. It turns out that if you want to see your signal to noise go up by a factor of 10, you can't just average 10 scans together. Oh no, you're going to have to average 100 scans together. That's right, 100 scans, because it's the square root. So if you want to see an S over N increase by 10, it's 100 spectrum. So think about this. You've got your beautiful IR there on the left, polystyrene film from Harris. How would we calculate the signal to noise in that? Look at those big, sharp, big old peaks. You got some nice ones between 2800 and 3200 wave numbers, and you've got all of those down there 1600 and below. You've even got some kind of shorter peaks around 2000. Now, are those signal? Well, the only way we know they're signal is if we can figure out what the noise is. Then we can calculate our S over N. How are we going to do that? That's what your job is. We're going to talk about some noise and some signal for a bit at the start of class on Monday. Think about your collected spectrum. How do you calculate the noise? Have you even looked at the noise? So think about your caffeine spectra. It's probably got a lambda max at about 272, 273. But you are collecting data from probably 500 nanometers. So if you were to zoom in and just plot the data between, say, 400 nanometers, 500 nanometers, where there's no absorption, and you zoomed way in, how noisy does it look? Is it really a flat line? Think about it. Think about that segment of your graph. How would you determine what the noise is then compared to the big old peaks or signals that you think you see? Come with some ideas and we'll discuss on Monday. See you then, and hope you're having a super weekend.